Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this revision video in which we'll go through everything you need to know for your upcoming exam. So I'm going to go through the topics on this slide here. Let's get straight into it by starting with equations. So each of these things in black that you see on your screen is an equation. It's an equation because it has an equal sign. What we want to do is solve equations. So that means we want to find a value that we can substitute for the pronumeral, the letter, usually x, to make this statement true. So how do we actually go about doing that? What we do is we undo everything that's been done to x, but we do this in the opposite order to BIDMAS, to the order of operations. So in this first one, you probably know what the answer is off the top of your head. So we've taken a number x, added 5, and got 13. So the way we're going to get x by itself, find out what it is, we're going to undo adding 5 by subtracting 5. So if I subtract 5 from both sides, I just get x equals 8. So that is the solution, because if I substitute 8 here, I get a true statement. 8 plus 5 equals 13. You can actually use that to check your answer. You don't need your teacher to tell you whether or not you're right. Get your answer, substitute in the equation, see if you get a true statement. So let's do this one here. This actually has two operations performed on x. So the order of operations says we've multiplied first, we've taken x, multiplied by -7, added 22 to get -6. So when we are undoing what's been done to x, we need to undo in the opposite order of operations. It's sort of like to get dressed in the morning, you put on your shirt and then your jumper, and then at the end of the night, you need to take your jumper off first because it's the last thing you put on. So here, adding 22 is the last thing we did, so we need to subtract 22 first. The reason we're subtracting 22 is I want to get rid of the 22 on this side. 22 minus 22, they cancel each other out. So I'm left with minus 7x equals minus 6 minus 22 is negative 28. So now I've got minus 7 times x. The way I'm going to undo timesing by minus 7 is dividing each side by minus 7. So I'm not dividing by 7, I'm dividing by minus 7. So times minus 7 and divide minus 7 cancel each other out. I'm left with x on the left-hand side. Negative 28 divided negative 7 is just positive 4. That's my solution. So once again, I can check. If I substitute x equals 4, I get 22 minus 7 times 4 equals minus 6. Well, 22 minus 28 does equal minus 6. I know I'm right. If I substitute x equals 4, I get a true statement. So let's look at this one with brackets. So what we're going to do is expand the brackets to make this a little easier to work with. So I distribute the 3 to the x by timesing. I distribute the 3 to the negative 4 by timesing. So 3 times x is 3x, 3 times negative 4 is 12, and I've still got my 27. I haven't actually started solving yet. So now I want to get x by itself by undoing everything that's been done to x. I've times x by 3, then subtracted 12 to get 27. So I'm going to undo subtracting 12 by adding 12 to both sides. I get 3x is equal to 39. 3x means 3 times x. So I undo timesing by 3 by dividing each side by 3. So times 3, divide 3, undo each other. I'm left with x equals 39 divided by 3, which is 13. Once again, I can check my answer by substituting x equals 13 into this equation. So if I do that, I get 3 times by x minus 4 equals 27. So, is this a true statement? Well, 13 minus 4 is 9. 3 times 9 is 27. Absolutely. True statement, so I know I'm right. So let's look at these two equations now. They probably look the same to you, but they're only different in their order of operations. Because a different order of operations has been performed here and here, the answers will be totally different. It's really important that we undo things in the opposite order of operations. If you mess up the order of operations, you get the answer wrong. In this one, x has been divided by 5, then 4 is added. Here, 4 is added, and then we've divided by 5. So, in this one here, because we added 4 last, it was the last thing we do, we're going to first subtract 4. Add 4, subtract 4, cancel. I'm left with x over 5 is equal to 8 minus 4 is 4. So this is x divided by 5. The way you undo dividing by 5 is timesing by 5. So when I times by 5, divide 5, and times 5 undo each other. The denominator's just gone. I'm just left with x equals 4 times 5, which is 20. So I can check my answer as I did in the previous 3. So here, I'm going to times by 5 first, because I added 4, then divided by 5. Dividing 5 is the last thing I did to x, so it's the first thing I undo. Once again, divide 5 and times 5 cancel each other out. I don't times the x by 5 and the 4 by 5. The divide 5 times 5 cancel each other out. So I'm left with x plus 4 equals 8 times 5 is equal to 40. So now I'm going to undo adding 4 by subtracting 4 from both sides. So, of course, I'm left with x equals 36. Once again, I could check my answer as I did in the first 3. So you can see the answer is totally different if I change the order of operations. So let's do this last one here. It's a bit tricky because I have x's on both sides of the equal sign, on the left-hand side and on the right-hand side. So what I'm going to do is I'm going to expand the brackets, then I'm going to get x to one side of the equation. So expanding the brackets, 4 times x is 4x, 4 times negative 4 is negative 16. So on the right-hand side, I go 5 times minus 5 is negative 25, and then 5 times minus x gives me minus 5x. So when you've got a situation like this, after you've got rid of brackets or fractions, if you have the x pronumeral on both sides of the equation, subtract the one with the lowest coefficient. So coefficient means number in front of. This x has a 4 in front, this x has a negative 5 in front. Negative 5 is lower than 4, so I'm going to subtract it. I'm going to subtract from both sides of this equation negative 5x. So always subtract the x from both sides of the equation. Of course, subtracting negative 5 is the same as adding. The idea here is if I add 5 to this side of the equation, I'm going to get rid of the minus 5x here. And then I will only have x's on one side of the equation. That's what I want. I want to get x to one side of the equation. Minus 5x plus 5x is 0. Just remember, I can't add 5x to minus 25. They're not like terms. You can only add or subtract like terms. So on the left-hand side, I can't add 5x to negative 16, but I can add 5x to 4x. 4x plus 5x is just 9x. So I have 9x minus 16 equals negative 25. So now I'm just going to solve like normal. I'm going to add 16 to both sides, and I get 9x is equal to minus 9. Then I'm going to divide each side by 9, because that's how I undo timesing 9. And I'm left with x is equal to minus 1. Once again, I could check my solution by substituting into the original equation and seeing if I get a true statement. If you do that, you'd get minus 20 on the left-hand side, you'd get minus 20 on the right-hand side. Everyone's happy, we've got it right. Let's look at some worded problems involving equations now. So let's start with this one here. Brad works at a clothes store, earns $25 per shift plus $4 per t-shirt sold. He earned $73 this shift. How many t-shirts did he sell? So when you're solving worded problems, always follow this process. Your first step is to define a variable. You start by letting x, or whichever letter you want, you let x be the thing you're trying to find. Here I'm trying to find how many t-shirts sold. So I'm going to let x be the number of t-shirts sold. So first step is to define a variable. Second step, we're going to turn the worded information into an equation. So $25 for the shift plus $4 per t-shirt. $4 times the number of t-shirts sold gave me $73. So I'm going to solve this just like I did the equations on the previous slide. Once we've got to this step and formed the equation, we've done all the hard work. So I'm going to subtract 25 from both sides, and then I'm going to divide each side by 4. So I found x equals 12. X was the number of t-shirts sold. So that means he sold 12 t-shirts. And I should always solve a worded problem with a worded answer. So let's look at this one here, which is a bit more tricky. Tom and Daniel scored all the goals for their football team. Daniel scored 3 fewer than double the amount Thomas scored. 39 goals have been scored. How many did each person score? So this is a bit tricky because we're finding how many each person scored. We're finding more than one quantity. Here there are 2 quantities. How many Tom scored, how many Daniel scored. So when that happens, I'm still going to define my variable. But I don't want to use 2 different letters, 2 different variables for the 2 quantities. So let's let x be the lower quantity. So Tom scored fewer goals. So let's let x equal the number of goals that Tom scored. What I don't want to do, I don't want to let y be the number that Daniel scored. The reason for this is because we don't know how to solve equations with more than one pronumeral. If you look on the previous slide and this example here, every example I've given you had only one pronumeral, which was x. We can't solve it with a second pronumeral. So instead of writing y as the number Daniel scored, we want to write the number that Daniel scored in terms of x. So if Tom scored x goals, then Daniel scored double the number that Tom scored minus 3. 2x minus 3 is the number of goals Daniel scored. So now we can form our equation. The number that Tom scored plus the number that Daniel scored is equal to 39. So let's make this easier to work with. X plus 2x is 3x. We're collecting like terms. So now we've got our equation, all the hard work is done. This is quite a challenging question, but we've reduced it to an easy one that we know how to do. We know how to solve this. What we're going to do is just add 3 to both sides and then divide each side by 3. So we get x equals 14, but x was the number of goals Tom scored. So we've just found that Tom scored 14 goals. So that means the number Daniel scored is 2 times 14 minus 3. Tom scored 14, Daniel scored 25. And you can see here that I'm solving a worded problem with a worded answer. All right, let's now move on to inequalities. So inequalities are very similar to equations. In fact, you solve them the same way. Equations, however, have an equal sign, and inequality has one of these signs here. So these 2 pointing to the right mean greater. These 2 pointing to the left mean less. This is greater than or equal to, less than, or equal to. So remember, the crocodile eats the larger number. So if we have something like 5 and 3, the crocodile eats the larger number. Think of this as a crocodile's mouth. So this says 5 is greater than 3. So we'll get inequalities like this that we have to solve. So how do we solve this? Well, we're going to solve this using the same process as for equations. So what I'm going to do is I'm going to start by timesing each side by 2 first. So remember, we don't times the top here. If I times the left-hand side by 2, times 2, divide 2, undo each other. So x plus 3 is greater than or equal to. That's what this says. So what I'm going to do is subtract 3 from both sides. And then I get x is greater than or equal to 2 minus 3 is minus 1. So same process, except instead of x equaling minus 1, we have x is greater than or equal to minus 1. There are infinitely many solutions here. If I substitute x equals 0, it makes this statement true. If I substitute x equals 1, it makes this statement true. X equals 2 would make this statement true. In fact, I can pick any number for x that is greater than or equal to minus 1, and it will be a solution. If I substitute x for any number that's either minus 1 or more than minus 1, it will make this statement true. So how would we do this one? Well, this is like the same process. We're going to start by subtracting 5 from both sides. So 2x is less than, so 3 minus 5 is minus 2, and we're going to divide each side by 2. We get x is less than minus 1. So this is saying I could substitute for x any number less than minus 1, and it would make this statement true. X equals minus 2 is a solution to this. X equals minus 3 is a solution to this. So why are these solutions? Well, if I substitute x equals minus 3, I get 2 times minus 3 plus 5 is less than 3. That is a true statement. Minus 6 plus 5 is less than 3. The thing is, though, unlike for equations where there was only one solution, here there are infinitely many solutions. I didn't have to choose minus 3 for x. I could have chosen any number less than minus 1. So after we've got our solutions with inequalities, we graph them on a number line to show the solutions visually. So we're going to graph this on a number line. So we're going to start by drawing up a number line. So we're talking about x is greater than minus 1. So let's just put minus 1 in the middle of our number line and a couple of numbers either side. Number line goes forever. So then, of course, on the other side, be like minus 2 and minus 3. So how do we graph x is greater than or equal to minus 1? Well, let's put a circle at minus 1. So we want all the numbers greater than minus 1, so we want to go this way. If you go to the right, the numbers get larger. So we just draw an arrow this way. So this thing here means you shade in the circle if it's a greater than or equal to or a less than or equal to. You don't shade in the circle if it doesn't have the little line under here, if it's just less than or greater than. So here, it's a greater than or equal to, so I'm going to shade in this circle. Shading in the circle shows me that I am including the value directly under. I'm including minus 1 here. So if I wanted to graph x is less than minus 1, it's actually sort of the same idea. I would rule up my number line, I would put minus 1 in the center, and I do a couple of numbers either side. So once again, I need arrows because the number line goes on forever. But when I'm graphing x is less than minus 1, I'm going to have an open circle because I'm not including that. Minus 1 is not a solution here. That's because if I take my original equation and sub in minus 1, I get 2 times minus 1 plus 5 is less than 3. This is saying 3, because 2 times minus 1 plus 5 is 3. 3 is less than 3. That's not true. 3 is not less than 3. X equals minus 1 is not a solution to this inequality. So that's why I have the open circle to show that I'm not including minus 1. I'm including everything that's less than minus 1, but not actually including minus 1. All right, let's move on now to fractions. So we're going to start by looking at equivalent fractions. So fractions are written as something over something, A over B or C over D. So two fractions are equivalent if A times D equals B times C. This means they have the same value. So they both equal the same decimal point. They both occupy the same position on the number line. The easiest way to think about it is two fractions are equivalent if what I do to the top, I do to the bottom. If I times the top numbers, which are the numerators, by the same thing that I times the denominators by. So that probably doesn't make heaps of sense. So let's look at an example in which we're simplifying fractions. You would have done this before. If I ask you to simplify a fraction, it means find an equivalent fraction with lower whole numbers. So let's look at 6 over 12. So what I do to simplify is divide by the highest common factor. The highest factor, the highest number that goes into both 6 and 12 is 6. So see how I'm dividing the numerator by 6 and the denominator by 6. Because what I'm doing to the top, I'm also doing to the bottom, this will be an equivalent fraction. 6 divided 6 is 1, 12 divided by 6 is 2. 6 over 12 is equivalent to a half. Both are equal to 0.5. It's just a half is simpler because it has lower numbers at the top and the bottom. So I can do the same 36 over 63. The highest number that goes into both of them is 9. So I'm going to divide top and bottom by 9. So 36 divided by 9 is 4. 63 divided by 9 is 7. These two fractions are equivalent. They're both equal to like 0.2857. Goes on forever. So the reason that they're equivalent, what I did to the top, I did to the bottom. I divided the top by 9, but I also divided the bottom by 9. So equivalent fractions can also be used to compare fractions. That means determining which fraction is larger. So if I have two fractions like this, 7 over 8 and 17 over 20, it's hard to know which is larger because they have different denominators. What I can do though is I can use equivalent fractions. I can find an equivalent fraction here, an equivalent fraction here that have the same denominator. Then comparing them will be really easy. So how do I know which denominator? What denominator do I make this? Well, I use the lowest common multiple. The lowest common multiple of 8 and 20 means the lowest number divisible by both 8 and 20. That's actually 40. What I'm going to do is find an equivalent fraction of 7 over 8 with denominator 40. I'm going to do the same to 17 over 20. I'm going to find an equivalent fraction whose denominator is 40. This fraction and this fraction will be easy to compare. So to go from 8 to 40, I times by 5. So if I want the fractions to be equivalent, I also need to times the top by 5. What I do to the bottom, I must do to the top. So if I've times the bottom by 5, I times the top by 5. I get 35 over 40. So in this fraction over here, to get from 20 to 40, I need to times by 2. So that means I also need to times the top by 2. So I get 34 over 40. You can see clearly 35 over 40 is larger than 34 over 40. So that means 7 over 8 is greater than 34 over 40, and we're done. Let's now look at some operations with fractions. So, of course, by operations with fractions, I'm talking about multiplication, division, addition, and subtraction. So multiplication is pretty simple. It's a lot easier than adding because you just need to multiply the numerators, which is the top numbers, and multiply the bottom numbers. So remember, of means times. So if I have 3/5 of 45, that's the same as 3/5 times 45. Now, if you have a whole number as a fraction, write it over 1. 45 and 45 over 1 are the same. So to do this, I just times the tops and times the bottoms. Now, 3 times 45, it's not easy without a calculator. Remember, you don't have a calculator for this test. I can make it easier by cancelling. 5 goes into itself once, 5 goes into 45 9 times. So I'm just left with 3 times 9 is 27 over 1. I don't even need to write the over 1. That just equals 27. So how do you do division? Well, when you're dividing fractions, you flip the second fraction and make it a times. So a whole number, 6, write it as 6 over 1. So what I'm going to do is I'm going to flip the second fraction and make this a times. Now it's just like the previous example. I times the top and I times the bottom. So 6 times 3 is 18, 1 times 1 is 1. Of course, 18 over 1 is just 18. I don't really need to write the over 1. So how would you do these ones? Well, this is a division, so I am going to have to flip the second fraction and make it a times. The problem is I can't flip 1 and 9/10, it's a mixed number. What I need to do first is make this and this an improper fraction. Improper fraction means the numerator, the top number, is larger than the bottom number. So I go 3 times 3 plus 1. That gives me 10. 3 1/3 is the same as 10 over 3. I do the same here. 1 times 10 is 10, plus 9 is 19. So this is 19 over 10. So 10 over 3 divided by 19 over 10. So what I'm going to do is I'm going to flip the second fraction and make it a times. Timesing is really simple. I just times the two top numbers and times the two bottom numbers. So 100 over 57, that's an improper fraction. If you wanted to, you could make that a mixed number. So to make a mixed number, how many times 57 go into 100? It goes once, remainder 43. So 1 and 43 over 57, and we're done. So that's multiplying and dividing. To multiply, just multiply the tops, multiply the bottoms. If it's a division, flip the second fraction and then make it a multiplication. So addition and subtraction is a little bit harder because you can only add or subtract fractions if the denominators are equal. That wasn't true when we were multiplying fractions. We could still multiply the fractions even if the denominators were different. Here the denominators have to be the same. So we're going to do what we did on the previous slide. We're going to use lowest common multiple to make each of these fractions have the same denominator. The lowest common multiple of 4 and 5 is 20. 4 times 5 is 20. 20 is the lowest number divisible by 4 and also divisible by 5. So I'm going to make 1 over 4. I'm going to times top and bottom by 5. 1/4 and 5 over 20 are equivalent fractions. Here, I'm going to times top and bottom by 4, so it becomes 4 over 20. 1/5 and 4 over 20 are equivalent fractions. So now that I've got the same denominator, all I can do is just add the numerator. 5 plus 4 is 9. I don't add the denominators. I only add the numerators and keep the same denominator. I don't go 20 plus 20 equals 40. So there we have it. 1/4 plus 1/5 is 9 over 20. So how would I do 7 over 8 minus 5 over 6? Same idea. I'm going to find the lowest common multiple of 8 and 6. Well, that's 24. So I'm going to times top and bottom here by 3. 8 times 3 is 24, so I times this by 3. I have to times this by 3. 7 over 8 is the same as 21 over 24. So for 5 over 6, I'm going to times the bottom by 4 to make its denominator 24, so I times the top by 4 as well. So 5 over 6 is the same as 20 over 24. 5 over 6 and 20 over 24 are equivalent fractions. So now I'm just going to subtract the numerators. 21 minus 20 is 1, and I keep the same denominator. So it's just 1 over 24. So here we are subtracting some mixed numbers. We could do what we did here and change both fractions, both mixed numbers, into improper fractions. You can do it that way. I could go 10 over 3 minus 19 over 10. Another way you can do it is like this. So with adding and subtracting, you can just do the whole number parts, the 3 and the 1, separately to the fractions. So I can write this as 3 minus 1, that's the whole number part, plus 1/3 minus 9/10. So 3 minus 1 is 2, that part. So to get this part, I need to do what I've been doing in the previous two examples. I need to make these two have the same denominator. So 1/3 is the same as 10 over 30, and 9/10 is the same as 27 over 30, because I times top and bottom here by 3. So now I've got 2. Now, 10 minus 27 is negative 17. So it's negative 17 over 30. So 2 minus 17 over 30 just leaves me with 1 and 13 over 30. So I chose to do the whole number part separately to the fractions, but I could have done this. I could have done 10 over 3 minus 19 over 10. And I would have got the same answer. So let's just look at a quick worded problem with fractions. So Connor, Will, and Tony share a pizza. Connor ate 2/3 of the pizza. Will ate 1/5. What fraction of the pizza is left? So let's calculate the fraction of pizza that's been eaten. So we have Connor, who ate 2/3, plus the 1/5 that Will ate. So if I want to add these up, I need these to have the same denominator. So I'm going to times top and bottom here by 5, top and bottom by 3. If I do this, both fractions will have a denominator of 3 times 5 is 15. 5 times 3 is 15. 15 is the lowest common multiple of 3 and 5. It's the lowest number divisible by 3 that's divisible by 5. So 2 over 3 is the same as 10 over 15. 1 over 5 is the same as 3 over 15. So adding these up, I just add the numerators. I get 13 over 15. So Will and Connor ate 13/15 of the pizza. So that, of course, means 2/15 will be left for Tony. All right, that's all for fractions. Let's move on to indices. So we're now looking at index laws, but let's understand what an index is. So something like 3 to the power of 4 means 3 times 3 times 3 times 3. It means you times this number, called the base, by itself this many times, which is called the index. This number here, the index or the power, tells you how many times you multiply this number by itself. So this is 3 to the power of 4. Because it has an index, because it's something to the power of something, it's called index form. Writing out 3 times 3 times 3 times 3 we call expanded form. And if you were asked to evaluate 3 to the power of 4, evaluate means give the answer. 3 to the power of 4 is actually equal to 81. But in the vast majority of questions, you won't be asked to evaluate. You won't be asked to give an expanded form. You'll be asked to write stuff in index form. So if you're asked to write something in index form, your answer needs to be something to the power of something. Because this power here is called an index, hence the name index laws. These are the 3 index laws we went through. So it looks a bit algebraic and complicated, but don't worry, it's really simple. This first index law says if you multiply the bases, add the powers. If you divide the bases, subtract the powers. And the third one says anything that's not 0 raised to the power of 0 is equal to 1. Okay, let's look at some examples. So simplify an index form. I want to write this as something to the power of something. So the first index law tells me when you're multiplying bases, you keep the same base. So 4 is the base we keep. And then we add the powers, 7 plus 8. And then we are done. So in this next one here, 10 to the power of 9 times 10, note 10 is the same as 10 to the power of 1, just like 4 and 4 to the power of 1 are the same. So we're going to use the first index law again. We keep the same base, so 10 is the base here, and we add the powers. 9 plus 1 is 10, and then we're done. So let's look at this example here. 2 to the power of 11 divided to the power of 6. Well, this is the second index law. If you have the same base and you're dividing, you keep the base and subtract the powers. So I'm just going to keep the base and subtract the powers. 11 minus 6 is 5. So how would we do something like this? Because we have 4s and 3s. Well, these index laws, the first 2 index laws, only work if you have the same base. So I can't times 4 and 3 together to get 12 to the power of 15. It doesn't work like that. What I have to do is I have to do the 2 4s separately. So these two have a base of 4. And then I have to do the 2 3s separately. I can only use these index laws when I have the same base. So 4 to the power of 7 divide 4 to the power of 2. So of course that's just 4 to the power of 5. Keep the same base. And then subtract the powers. So then I times by, I've got 3s now. 3 to the power of 8 divide 3 to the power of 5. So because this 3 to the power of 5 is in the brackets, it's being divided. So 3 to the power of 8 divide 3 to the power of 5. Keep the same base and subtract the powers. And then we're done. All of these are in index form because they've got something to the power of something. So evaluate, as I set up here, means give the answer. So if I have 3 to the power of 0, it's just 1. Anything to the power of 0 is 1. So the reason for that is 3 to the power of 0, well, that's just 3 squared, for example, divide 3 squared. The index laws tell us 3 squared divided by 3 squared. You keep the same base and subtract the powers. 2 minus 2 is 0. But 3 squared is just 9. And we know 9 divided by 9 is equal to 1. So I could have used any numbers here. That's just a quick explanation as to why anything to the power of 0 is 1, as long as it's not 0. That's because anything that's not 0 divided by itself equals 1. So this one's a bit more tricky. So here, remember, order of operations, we're going to do what's in the brackets first. So this is 4 times 2 is 8 to the power of 0. So 8 to the power of 0 is 1. For this term here, 4 times 2 to the power of 0, no brackets means we do raise to the power first. Index comes before multiplication in BIDMAS. 2 to the power of 0 is 1. So this is just 4 times 2 to the power of 0, which is 1. 1 plus 4 times 1, 1 plus 4 is equal to 5. So which number would go in the box in this expression here? So we know 4 to the power of 12 times 4 to the power of 5 is 4 to the power of 17. So I can just write that a little more simply. So what number do I need to put in the box? Well, I need to realize 4 is the same as 4 to the power of 1. So remember, when we divide bases, the base here being 4, we subtract the power. So I'm saying, what do I subtract from 17 to get 1? And of course, the answer to that is 16. Because 17 minus 16 is equal to 1. When I divide bases, I subtract the powers. All right, that's all for indices. Let's go on now to linear relations. So in linear relations, you basically need to be able to plot straight lines, calculate gradients, and find the equation of the line. So we'll start with plotting straight lines. So what you'll do is you'll get an equation like this in the form y equals mx plus b and turn it into a graph. So if the equation is y equals something times x plus something, then the graph will be a straight line. So how do we actually graph it? Well, we get our equation and we draw up what's called a table of values. So what we're going to do is we're going to pick the x values, so some positive and some negative. So I'm going to pick x values, a few negatives, and then some positives. So I haven't done any calculations here. I've just chosen these x values. What we do with the x values is one by one, we substitute in the equation to find the corresponding y value. So if x is minus 2, y is 5 minus minus 2, which is 5 plus 2, or 7. If x is minus 1, y is 5 minus minus 1, which is 6. If x is 0, y is 5 minus 0, which equals 5. You can probably see a pattern. Y is going down by 1 each time. So that's not a coincidence. That's because this number in front of x is 1. Minus x and minus 1x are the same thing. So what we have here is a table of values. Each of these columns is a point. This is a point because it has an x and a y value. This is the point minus 2, 7. So what we're going to do is we're going to go to our Cartesian plane and plot them. So remember, the y-axis is always the vertical axis. The x is the horizontal. When we write points, we always write x first. So I'm going to plot the point minus 2, 7. So I go across to x is minus 2, which is here, and I go up to y is 7 here. So all I'm going to do is plot that point where x is minus 2 and y is 7. So I'm going to do the same for all the other points. The next point I'm going to plot is the point minus 1, 6. X is minus 1, y is 6. So I go across to x is minus 1, which is here, and up to y is 6, which is there. So minus 1, 6 is the point there. And then I'm going to do the same for all the others. The next point is 0, 5, 1, 4, 2, 3, and then 3, 2. You can see all of these points lie in a straight line. So to plot the line, I'm just going to join up these points. So I need to put arrows on the end of my line because the line goes on forever. I could have substituted x equals 4, 5, 6. It just keeps going. So here you can see I've drawn the straight line, and the last thing I'm going to do is I'm going to write the equation of this line. Y equals 5 minus x. So if you're given an equation and told to make it into a graph, what you do is draw up a table of values. You pick the x values, some positive, some negative. You substitute each value into the equation to find the corresponding y value. And each of these columns is a point that you plot in the Cartesian plane, which is this thing here. and then you just join up the points. I know there's a lot of steps in that, but just go over this again and again until you get it. We're going to move on now to gradient. So the gradient of a line is a measure of its steepness. So the gradient of a line is just a number. The higher the number, the steeper or more vertical the line is. So let's look at these two lines here. You can see the green one is steeper than the yellow one. So the green one would have a larger gradient than the yellow one. So both of these lines lean to the right. So compared with a perfectly vertical line like that, you can see that they lean to the right. If the line leans to the right, then m is greater than 0. For some reason, m is what we use to denote the gradient. So m is greater than 0 means gradient is positive. If the line leans to the right, the gradient is positive. If the line leans to the left, like these two lines, the gradient is negative. If the line is perfectly flat, perfectly horizontal, the gradient is equal to 0. So the gradient is a measure of steepness. It's a number that tells you how vertical the line is, but how do we actually calculate the gradient? Well, you can use either of these formulas. The gradient is the rise over the run. So the rise is how far you go up, and the run is how far you go down. That's what the gradient is. Another way is y2 minus y1 over x2 minus x1. So y2 is just y coordinate of the second point, y coordinate of the first point, x coordinate of the second point, x coordinate of the first point. So it might not be making a lot of sense, but hopefully it will in a second after we calculate the gradient of the blue and the green lines. So we're going to start by calculating the gradient of the blue line. So to do rise over run, or this formula, you need 2 points. So I've plotted 2 points here. So this point here is the point x equals 1, y equals 1. And then this point here is the point x equals 2, y equals 3. So how do you calculate rise over run? So what you do is you start at the leftmost point and you go to the right. So to go from this first point here to this second point here, I go 1 to the right and 2 up. So the gradient is rise over run. The rise is 2. From this point to this point, I've gone up 2. So the rise is 2, and I've gone 1 to the right. I've gone across 1, so the run is 1. So that's using rise over run. If I wanted to use y2 minus y1, what I do is this. I go, the y coordinate of the second point is 3. The y coordinate of the first point is 1, divided by x coordinate of the first point is 2, and x coordinate of the second point is 1. So what I did here to use this formula is I used the points 1, 1, and the points 2, 3. So substituting into the formula, this, remember x is always written first. This was x1, x coordinate of the first point, y coordinate of the first point, x coordinate of the second point, and y coordinate of the second point. I just substituted in these values. y2 minus y1 over x2 minus x1. And I get the exact same answer. I get 2 over 1, which is 2. The gradient of the blue line is 2, and you got the same answer whether you use this formula or rise over run. So let's now look at calculating the gradient of the green line. Once again, m means gradient. So I have 2 points, 1 here and 1 here. I said always start at the leftmost point, so that one is here. So go from the left to the right. We're going from this point to this point, and we're going across 2. We're going from x is minus 1 across 2. And then we're actually going down 1. So what would the gradient of this line be? Well, using rise over run, we've gone down 1. So when you go down, it's negative gradient. You know that the gradient of this line in green should be negative because it leans to the left. The gradient of the blue line was positive because it leaned to the right, but this gradient's negative. So we put a negative run, negative on top because we went down, we didn't go up. You always go to the right. The gradient's positive if you go up. The gradient's negative if you then go down. The rise here is negative because we've gone down. So the run is always positive. We always go to the right. It's 2. The gradient is negative 1/2. So we would have got the exact same answer if we used this formula here. So the first point over here is the point -1, 1. And the second point, so remember we always list x first, and the second point, this point here, is the point 1, 0. We would have got the same answer, because we would have gone y2, y coordinate of the second point, minus y coordinate of the first point, over x2, x coordinate of the second point, minus x1. So here we'd have to do minus 1. We would get the same answer of -1/2 either way. So the gradient of the green line is -1/2. You can see that that gradient is less than the gradient of the blue line because the blue line is steeper or more vertical. All right, the final thing we have to do is finding the equation of a line. So, in this slide, we are going to find the equation of these 3 lines. You're probably thinking to yourself, wait, I don't actually see 3 lines. Well, what we're doing is we're going to find the equation of the line that would go through all of these points, the equation of the line that would go through all of these points, and the equation of the line that would go through all of these points. Another way to look at it is for each of these table of values, we're going to find an equation that links x and y. We're going to find an equation that tells us how you get the y value if you know the x value. So that equation is always going to look like this. It's always going to be y equals something times x plus something. Now remember, m is the gradient. So the gradient is what we looked at on the previous slide. This number here, b, is the y-intercept. So the y-intercept of a line is where it hits the y-axis. So for this blue line here, it has a y-intercept of 2. So how do you find the y-intercept from a table of values? Well, along here, the x-coordinate is 0. See, this point here is the point 0, 2. The y-intercept is the y value when x equals 0. So to find this number here, it's exactly that. It's the y value when x equals 0. So let's look at this first table of values here. We're going to find the equation linking x and y. So it's going to be y equals something times x, gradient times x, plus y-intercept. So, what is the gradient? Well, the gradient is the rise over the run. Another way to look at the gradient, it is the number that y increases or decreases by each time x increases by 1. So, each time here you can see x is going up by 1, y is also going up by 1. So that means the gradient is 1. So finding the y-intercept is actually really simple. Finding this number here, it's just the y value when x equals 0. So this one here. So now I can change b, the y-intercept, to 5. So the equation of this line is y equals 1x plus 5 or y equals x plus 5. And that makes sense. To get the y value, you just take the x value and add 5. Add 5, add 5, add 5, add 5. Add 5. So we're done. All right, let's do the next one here. So here, each time x is going up by 1, y is actually going down by 2. So remember, down for y means a negative gradient. So here, the gradient is actually -2. So the number that goes in front of x is -2 because we're going down by 2 each time. The number that goes by itself, the other number in the equation, is the y value when x equals 0. The equation of this line is just y equals minus 2x minus 1. So if I times x by minus 2 and then subtract 1, I get the y value. Minus 2 times minus 1, subtract 1 gives you 3. You know, minus 2 times 2, subtract 1 gives you minus 5. This equation tells you how to get the y value from the x value. So let's look at this one here, which is a little harder. So here, it's harder because x isn't going up by 1 each time. It's actually going up by 4 each time. What's happening with y is it is actually going up by 12 each time. So you're probably tempted to think the gradient is 12, but that's not true. The gradient is the number that y increases or decreases each time x goes up by 1. So each time x goes up by 4, y goes up by 12. So that means each time x goes up by 1, y goes up by 12 divided by 4. This is just rise over the run. The rise is just the change in the y values, how much y values are going up by, because the difference in y values is how far we go up. And the run is the change in x values, because it's just how far we're going across here. So the gradient here is 12 divided by 4, which is 3. Each time x goes up by 4, y goes up by 12. So if x were to go up by 1, y would go up by 3. So that's the gradient, but what would be the y-intercept? Well, because we now know the gradient, we know that each time x goes up by 1, y goes up by 3, I can add in a few more values to this table. If x were to be minus 1, y would be 10 plus 3, which is 13. And if x were 0, y would be 13 plus 3, which is 16. So the y-intercept here would actually be 16. So the equation is y equals gradient times x plus the y-intercept. So remember, the y-intercept is just the y value when x is 0. The gradient, which is the same as what we learned on the previous slide, it's rise over run. It is how much the y values are going up or down each time x values are going up by 1. All right, thank you so much for tuning into this video. Best of luck in the test, but you'll be fine. You're a superstar. This has been the luckiest maths teacher in the world. Have a great day.